Hello, I'm Xu Zhiyao, and my student ID is CST2509050. Our group will present measuring the area covered by a radar system. Before discussing the mathematical model, let's first understand what radar is. Radar stands for radio detection and ranging. It uses electromagnetic radio waves to detect and track objects. By analyzing the reflected signals, radar can determine an object's distance, direction, altitude, and speed. So, how does radar work? First, the radar transmits radio waves. When the waves hit an object, such as an aircraft, they are reflected back to the radar. The radar then processes these signals to calculate the aircraft's position. For this project, we focus on airport surveillance radar, which monitors aircraft around an airport. Airport surveillance radar has several important applications. It detects aircraft within its scanning range, monitors their positions in real life, assists air traffic controllers, and helps prevent collisions to improve aviation safety. Because of these functions, airport surveillance radar is the real-world application used in our project. Since radar is responsible for monitoring aircraft, it is important to know how much area it can cover. Measuring the coverage area helps ensure that all aircraft can be detected and reduces blind spots. It also helps engineers determine the optimal scanning range while reducing installation and maintenance costs. Overall, accurate coverage analysis improves both safety and operational efficiency. Based on these needs, our project has four objectives. First, we will develop a mathematical model of the radar coverage. Second, we will represent the coverage using polar coordinates. Third, we will calculate the coverage area using calculus 2. Finally, we will analyze how the radar's range and scanning angle affect the covered area. We choose polar coordinates because radar locates objects using distance r and direction theta, making them the most suitable mathematical model for this problem. Now, I would like to hand over to the next presenter, who will explain the calculus 2 concept and develop the mathematical model. Thank you.
In this part, I will introduce the calculus 2 concepts used to measure the area covered by a radar system. There are three main concepts involved. The first is polar coordinates, unlike Cartesian coordinates, which use the x-axis and y-axis to locate a point. Polar coordinates describe a point using its distance from the origin, represented by r, and its angle from the positive x-axis, represented by theta. The relationship between the two coordinate systems is shown by the equations x equals r cosine theta and y equals r sine theta. The second concept is the area element in polar coordinates. In Cartesian coordinates, the area element is dx dy. However, in polar coordinates, the area element becomes r dr d theta. The extra factor r accounts for the increasing distance from the origin as the angle changes. The third concept is double integrals. A double integral allows us to calculate the total area of a two-dimensional region. Since the radar covers the region on a plane, double integration is an appropriate mathematical tool for finding the coverage area. Now, let's discuss why polar coordinates are used in this problem. A radar system is usually placed at a fixed location and sends out signals in all directions. It measures both the distance to an object and the direction of the object. Therefore, every point detected by the radar can naturally be represented by the pair r theta, because the radar scans in a circular or sector-shaped pattern. Polar coordinates match the geometry of the problem much better than Cartesian coordinates. If we use Cartesian coordinates, the boundaries of the region become more complicated and the integration process is more difficult. On the other hand, polar coordinates provide simple limits for both the radius and the angle. This makes the mathematical model easier to build and the calculations more efficient. For these reasons, polar coordinates are the most suitable coordinate system for analyzing radar coverage. Finally, let's look at the mathematical model. We assume that the radar has a maximal scanning range of R and it rotates from angle θ1 to θ2. Based on these assumptions, the covered region is defined by two simple conditions. The radius ranges from 0 to R and the angle ranges from θ1 to θ2. Using the area element in polar coordinates, we can express the total coverage area as a double integral. First, we integrate with respect to the radius and then with respect to the angle. After performing the integration, we obtain the final formula: A equals 1/2 R squared times the quantity θ2 minus θ1. This formula shows that the radar coverage depends on two factors: the maximal scanning distance and the scanning angle. In conclusion, by combining polar coordinates with double integrals, we can develop a simple and effective mathematical model for calculating the area covered by a radar system. Thank you for listening.
I'm Fan Zhihan, CST2509011. Today my group researches practical use of polar coordinates, and my part explaining a real-world radar coverage calculation example. Coastal radar stations rely on polar coordinates to describe their scanning zone perfectly. Cartesian coordinates will make this calculation more cumbersome. I will walk through a complete simple problem step by step now. Let me state the problem background first. A coastal radar sits at the origin of the polar coordinate system. Its direction boundary follows the polar equation R equals to 4 cosine theta. The unit of radial distance R is kilometers. The angle constraint is this, and our target is solving the total covered hard land area of this radar device. For curve area calculation, the standard integral formula is this. On step 1, substitute the given curve and the integral bounds into the formula. And step 2, expand the equal term. Simplify the expression to get this. And step 3, apply the double angle identity. For power reduction, the formula updates to this. Step 4, solve the antiderivative. And step 5, substitute the upper and the lower integral limits. The sign terms evaluated to 0. The remaining arithmetic outputs A equals to 4 pi, approximately equals to this. And from this case, we observe polar integrals greatly streamline area calculation for radial scanning equipment like radars. Engineers adopt this computing method to assess surveillance range and optimize radar deployment. That's all for my example explanation. Thank you for listening.
Hello, my name is Chen Shiman. My student ID is CST2509005. In the following part, I will explain the result analysis of our radar coverage model. Based on calculation, the radar covers an area of 4 pi, approximately 12.57 square kilometers, which means the radar can effectively detect objects within this coverage area. Any aircraft or ship entering this region can be monitored. Then let's look at the practical implications and limitations of this model. The calculated area is useful for planning coastal surveillance. It helps engineers determine the best locations and quantities of radar stations, improve monitoring efficiency, and reduce unnecessary installation costs. It can support applications such as maritime navigation, coastal security, and search and rescue operations. However, it has several limitations. For example, it assumes ideal conditions where the radar follows the equation r equals to 4 cosine theta. But in reality, weather conditions such as heavy rain or storms may affect radar signals. It also ignores obstacles like mountains, buildings, or large ships that may block the radar signal and reduce the actual coverage area. In addition, our model only considers two-dimensional coverage and doesn't account for the height of aircraft or other three-dimensional factors. So, to make the model more realistic, several improvements can be considered. First, environmental factors such as weather and terrain could be included in the mathematical model. Second, using multiple radar stations would reduce blind spots and improve overall coverage area. Third, a three-dimensional coverage model could be developed to consider the altitude of aircraft instead of only two-dimensional coverage. Finally, rather than assuming a fixed detection range, the model could use a variable radar range that changes according to environmental conditions or radar performance. Now, why are polar coordinates the best choice for this problem? Because a radar scans outward from a fixed reference point, which naturally matches the origin in polar coordinates. And objects are measured by the direction and the distance from the radar station, exactly the two variables used in polar coordinates. Besides, compared with Cartesian coordinates, polar coordinates simplify the calculation of coverage areas. As a result, they provide a direct mathematical representation of radar scanning patterns, making both modeling and analysis more efficient. Although the model is simplified, it clearly shows how calculus and polar coordinates can be applied to solve real engineering problems. Overall, polar coordinates provide an accurate and efficient way to analyze radar coverage, making them an essential mathematical tool in the design and planning of radar systems. That's all for our presentation. Thank you.